Using the view factor formulas that we discussed, we can set up equations for radiative exchange between surfaces. Let us consider radiative exchange between two black surfaces. That's about the simplest situation that we can do. We want to derive a formula for the net amount reaching from surface 1, that's this one, to surface 2. So this formula is given by Q1 to 2, the net amount of radiative heat going from 1 to 2 is equal to this quantity. Okay, but we're not just going to use the formula, we'll see where it comes from. So radiation from 1 to 2 is equal to, first, sigma T1 to the 4 is in watts per meter square that leaves surface 1. That multiplied by A1 is the watts. So this is the watts leaving area 1. How much of that would be reaching 2? This has to be multiplied by the view factor. So because view factor says, by definition, it's the fraction of this energy that will be intercepted by 2. Okay, so this is radiation from 1 to 2. This is not the net amount going from 1 to 2 because 2 is also radiating. So radiation from 2 to 1 is equal to sigma T2 to the 4 times A2 times F21, fraction of energy emitted by 2 that would be intercepted by 1. So that fraction is given by F21. So 2 may be getting this amount, but then it is also giving back this. So the net amount that goes from 1 to 2 would be the difference. That's what you see here. Okay, so 1 to 2, and this is 2 to 1. And so the difference is the net amount going from 1 to 2. And now, as I mentioned earlier, from geometric calculations, we can show that this is always true. A1 F12 is equal to A2 F21. So if I use that to replace this A2 F21 by A1 F12, then we get the final formula. So again, two important things. Q12 is the net amount of radiation going from surface 1 to surface 2 when the temperatures are these. The second thing is very important, that this is the net amount, so it has an implied direction. So its direction is 1 to 2. Okay, this is very important. We would need these for energy balance calculations. So we are now going to use the formula just derived to find the solar radiation incident on Earth. So this would be an alternate calculation of something we had already done. So here is the sun that's radiating in all directions, and only a small part of it is going to be intercepted by the Earth's surface, and we want to know what is the energy incident per unit area of this surface. So we write the energy balance equation that we just derived. So Q sun to earth, so you can think of this is 1, this is 2, so this is like 1 to 2, Q1 to 2 is equal to sigma A1, that is A sun, F sun to earth, so that's F12, so this is A1 F12 times T1 to the 4 minus T2 to the 4, so T sun to the 4 minus T earth to the 4. Now compared to sun temperature, earth temperature is very little, so we can drop this term and we can write sigma T sun raised to the 4, and then we can change, like we said a number of times, that A1 F12 is equal to A2 F21. So I can change from A sun to view factor sun to earth, change it to A area of earth, and then view factor earth to sun. This is the reason we did this, is this view factor earth to sun, that is from a small area to a sphere, is something we derived. So we're going to use this view factor. So the amount incident on earth per unit area of earth is equal to sigma F earth to sun times T sun raised to the power 4. Now F earth to sun, as I said, using a sphere and a small area, this is something we derived, the view factor, and that's simply equal to this the radius over distance squared. So if we now plug in the numbers, we get the same answer as we did from simple geometry calculation. So the simple geometry calculation was, we said whatever energy is coming out here is the same amount of energy is coming out over a sphere of this radius. If we just do it that way, we get the same value, which means this view factor is really, in this case, taking care of this distance effect. So the formula that we just derived for radiative heat exchange between two black bodies can be further simplified for a very special situation when temperature difference is small. So this is the formula we are talking about. That's for black bodies at two different temperatures, T1 and T2. Notice that the temperatures are raised to the 4th power. Thus, even small differences in temperature would cause a significant difference in these two terms. So this, what we are about to do, is true only for small temperature difference. Basically, we are going to linearize this term here. This term we are going to linearize. So when T1 is close to T2, let's call T1 minus T2 equal to delta T. So T2 equal to T1 minus delta T. And so let's plug this one in, and let's go slow in the derivation. So Q12 equal to T1 minus T1 minus delta T raised to the power 4, and we're going to expand this in two stages. So first we'll do T1 minus T2 square, and then we'll square it again. So T1 minus delta T square would be T1 square minus 2T1 delta 2 plus delta T square, but where we use the information that delta T is small is here. So we say because delta T is small, its squared form is going to be much smaller than the other two terms, and therefore we can neglect this third term. So that lets us keep the first two terms here, and then we square it again. We get three terms, and we use the same logic that the term with del T squared is negligible compared to the other two terms. So we keep the other two terms. So that gives us, because these two cancel, then we get sigma A1 F12 4T1 delta T, and then we combine this sigma times 4T1 cube into something called HR. We will explain in a second why we are doing this, but using this definition of HR, we can write the heat transfer to be equal to this. And for an even special case, of one body surrounded by the other. So if you have surface 1 and then this is surface 2, okay, and we're doing this kind of exchange. So for this, F1 to 2 is 1 because all the radiation from 1 is intercepted by 2. So the example would be, a small thing surrounded by another surface or surfaces of the same temperature, something like that. It's an approximation. So for this case, then our formula that we derived is Q1 to 2 is equal to HR A1 delta T. So this is for radiation. Okay, but from convective heat transfer, so for convection we have this formula, Q1 to 2 is equal to H times A times Ts minus T infinity, or we can think of this delta T as T1 minus T2. Okay, so what do you see? You see that our radiation formula looks a lot like the convection formula. Remember, this is for a very, very special case of radiation, but nevertheless, for this special case, it looks very much like the convection formula. So this HR, we can call it as a radiative heat transfer coefficient. So if we do it that way, then for this special case, radiation and convection have similar formula, and we may be able to compare the H values for these two very different processes. We're going to do that next, But remind you that this formula for radiation has many restrictions. This has many restrictions. So in general, it is not used very widely because it's way too simplified. We are going to use the very simple radiative formula that we just derived to do a quick comparison between radiative and natural convective heat losses from the human body. So first we do the radiative heat loss calculation. So the radiative heat transfer coefficient, as we defined, let's plug in the values. So if we take an approximate skin temperature of 32 degrees C, so remember our skin surface is cooler than the core body temperature. So if we plug in 32 plus 273, all these are quick approximate calculations, and plug in for sigma, this gives us radiative heat transfer coefficient of about 6 or 7 watts per meter square per degrees Kelvin. So how does it compare with convection? In particular, this is going to be compared with free convection, because forced convection there is no limit, we don't have any control, but free convection is when we have difficulty rejecting as much heat. So free convection, if you recall from the chapter of convection, the convective heat transfer coefficients for different situations typically are in this range typically. Okay, so free convection is typically in this range of 3 to 3 4 maybe to 30, something like that. So then when you do not have much airflow, then you'd probably be on the lower side. So which means what? It's 6, 7, 8, something like that. So that's very comparable to the radiative heat transfer coefficient. So the convective heat transfer coefficient, remember these are heat transfer coefficient, those values are comparable for radiative heat transfer coefficient for heat loss from a body surface. Now, if you look at literature for thermal comfort, then when they talk about human heat loss, it's of course made up of conduction, convection, radiation, and evaporation. But notice convection and radiation, it's about equal heat loss. Well, that's certainly what we see, that the convective heat loss and or convective heat transfer coefficient for convective heat loss and radiative heat transfer coefficient for radiative heat loss are about the same order of magnitude. So this kind of justifies what we normally see or have been reported, that convective loss and radiative losses are about equal. So we move to situations that are slightly more complex. When we have multiple black surfaces, for example here we have not just two black surfaces, but we have multiple surfaces forming an enclosure. We can handle this one using the black body exchange formula that we derived. So this formula is between any two surfaces. So in case of multiple surfaces that are all black, we basically reuse this equation between pairs of surfaces. So the net heat exchange from the surface I, Qi, so this is the net amount leaving surface I, net amount, what would it be? So let's take the first two, I and K. So it will be, following this equation, it will be sigma times AI times the view factor F between I and K, okay, times Ti raised to the power 4 like T1 and Tk raised to the power 4 like T2. So this would be between I and K, and we just sum them up over all the surface. Of course, K is not equal to I. We're not talking about exchange between itself, with itself, okay? So then this equation can give the net amount leaving surface I. So this is the net amount leaving surface I. Now we were able to kind of add the black body formulas. We're able to get away with it because they're black, because there's no reflection. If the surfaces were gray, so there is reflection, notice things will get complicated in a hurry. So then the exchange from here, so the radiative, the radiation leaving this surface when it is incident on the other surface, if this were gray, then part of it is going to be reflected. And we have to keep track of that. And that reflected part, when it hits this surface, again, parts of it is going to be reflected. And so we have to keep track of all of these if they were gray. So this is not, this equation for multiple surfaces forming an enclosure is not for gray surface. It's for black surface only, where there's no reflection from the surfaces. We will now try to extend the formulas to gray surfaces where there are reflections from the surfaces and absorptivity or emissivity are not equal to 1. But as I said, things get complicated with reflections. So the only case we can do in this simplified radiative heat transfer class is a two-surface enclosure. So what's a two-surface enclosure? So here, this is a problem that we're going to do later. It's a greenhouse that has these two surfaces forming an enclosure. We'll do a problem later on. For such two-surface enclosure, we can derive, we will not derive, but we can derive the expression that is provided to you here. So Q1 to 2 is the net heat transfer from surface 1 to surface 2, and that's related to all these quantities. Here epsilon 1 is the emissivity of surface 1. So if this is 1 and this is 2, then epsilon 1 is emissivity of surface 1, and then epsilon 2 is the emissivity of surface 2, and these are the respective areas. And then finally, then this one is the view factor between 1 and 2. Okay, and of course T1 is the temperature for surface 1 and T2 is the temperature for surface 2. So to repeat, Q12 is the net amount going from 1 to 2. So there's radiation going from 1 to 2 and coming from 2 to 1. But this is the net amount that's going from 1 to 2. Now, in an energy balance, it is very important to keep this direction implied in Q12 in mind. So, for example, in an energy balance for surface 2, if you're doing an energy balance for surface 2, then this term will be in. So, because it's going from 1 to 2. If you're doing the energy balance on surface 1, then this term is out because it's going from 1 to 2. It's leaving 1. Okay, so here we go to even more special case, but keeping it gray. We still have gray surfaces, and here also gray. So if we think of a situation like this, where this is 1, and it's completely surrounded by a surface that is 2, okay? When that happens, then of course F1, 2 equal to 1. But also we put the additional restriction that A1 is much less than A2. So this would be like we standing here in an empty room. Okay, so our surface area A1 would be much smaller than the surface area of the room. So A1 is much less than A2. So let's try to simplify this expression. So Q12 is equal to sigma T1 to the 4 minus T2 to the 4 1 minus epsilon 1, and I multiply throughout. In the denominator, I multiply throughout the numerator of the bottom part of the fraction. Numerator I multiply throughout by A1. So this is all multiplied by A1. So I get epsilon 1 minus epsilon 1 over epsilon 1 plus 1 over F12 plus 1 minus epsilon 2 over epsilon 2 times A1 over A2. Okay, so now we use the fact that A1 over A2 is very small, so we drop this term, and then this is equal to 1. So it will be 1 minus epsilon 1 over epsilon 1 plus 1. So if you add, you get sigma times epsilon 1 times T1 4 minus T2 to the 4, and since we multiplied here by A1, so we have to have multiplied this one also by A1, so that will give us the A1. So sigma times epsilon 1 A1 T1 minus. So this is the case. When can I use this? So this is two surface enclosure, one surface being much smaller than the other surface, and then they can be gray because you see there's an emissivity involved. Okay, so that is the last case that we are going to do.